Good day, friends. Welcome to another GeoGebra class. In this particular GeoGebra class, we want to learn certain things. So we want to visualize certain things that can be found in circle theorem and then certain theorems that we know in triangles. So the first thing we'll look at is the term that the sum of all the angles in a triangle is equal to 180 degrees. Okay, we are going to visualize it and see a graphical proof of why the sum of all the angles in a triangle is always equal to 180 degrees. Then we'll look at some theorems in circle theorem, okay? We'll look at some of the theorems there as well, maybe two or three of them. And then we'll look at the Pythagoras theorem and then a simple graphical proof of the Pythagoras theorem as well, okay? So let's not waste time. Let's begin with the proof of the sum of the angles of a triangle is equal to 180 degrees. So since we are proving triangle, let's use our polygon tool to draw a triangle right here. So it doesn't necessarily have to be a particular type of triangle. It's just random. We don't know whether this is isosceles or scalene or equilateral. It's just a random triangle, sorry. So, but when you come to the algebra view, you can see that all the sides are different. Okay, A is 6, B is 5.66, and C is 4.47. So in this particular case, that means that the triangle we have here is what? A scalene triangle, because all the sides are not the same, and therefore all the angles are also not the same. Okay, but this proof will work whether you have an equilateral triangle or an isosceles triangle. Still going to work. Even a right angle triangle is still going to work. So regardless of the triangle, this proof is going to work. All right, so to do the proof, this is a graphical proof of it. So we are not calculating, we are just showing it on a graph sheet. So we're going to use a circle with center and radius. Then at each of the vertices, we are going to create a unit circle. So here we create a unit circle. Unit circle is a circle with a radius of 1. So the center is the vertex, then the radius is 1. Then once we have this, we are going to go to our intersect tool under point. Then we'll find the intersection of each line of the triangle, each side of the triangle, and the unit circles. So you have to do this for each of them. Each line, you find the point of intersection of each line and the unit circle. So we have them, so 2 here, 2 here, 2 here, that's 6 in total. Then after that, we can just remove the circles by selecting them from the algebra view. Then come to the circle tool and select circular sector. And we need to draw this such that we'll have a circular sector inside. So we need a circular sector inside the triangle. So this is one of them. Then we do one also here. Okay. And then the last one here. So, okay, this is external. We want internal. So let's go anti-clockwise. So this and that's okay. So we have selected. So what we did here is that we have selected the angles. Okay. I've selected the angles, but we don't care about the value of these angles yet. Okay, all we care about is selecting them like this. Okay, so I can actually, okay, let me go here. I can actually now change the color of this to green and change the color of this to red. Okay, let me go the inverse of that. So this rather to green, this rather to red. And this to yellow. So I'm using the colors of our flag. So we have red, yellow, green. Okay, so we finished with the first step. So all that we have done is to select the angles. Okay, we have selected the angles. Now the next step is so we are just removing the points because we don't need them again now. So we are going to midpoints. We're going to find the midpoint to under midpoints. You find midpoints there and find the midpoint of this side and this side. We don't need the midpoint of the base. We only need the midpoint of this side and this side. Now I can create a line segment here that is parallel to the base of this triangle. Okay, you see the purpose of that in a bit. But I'm just going to create a segment at A that is parallel to the base of the triangle. Now, since I created this base using a line that is part of the grid, okay, so to create a line parallel to that, I just look at the parallel line, okay, that passes through A using the grid. So I'll just put a point here and then pass through A, then I'll put the other one somewhere here. Okay, so this one will definitely be parallel to this because I use the grid. Then I use the grid. Okay, so if you didn't have a grid, then you would have used parallel line to find the parallel line of this line at this point. Then you can create a line segment on that line you have gotten. Okay, and that will work. So to do that, you just come to parallel lines and then click on this line, the base of the triangle, and then the point, and then you see it has created a parallel line there. So once you get a parallel line, then you can now create the segments by putting the points on the line. Okay, but because we have the grid here, we can just use the grid to get a line segment, and you see it is accurate. So we don't need the line, so let's just remove the line, delete it. Okay, we only need the line segments. All right, now we have the midpoint, we have the line segments. Now to make it more beautiful, we are going to insert a slider. So slider, angle, so the angle alpha, animation is oscillation. Okay, that's okay. So the interval is from 0 to 180 degrees. Okay, and the increment one is okay. So we press on okay. So what we are trying to do is I'm trying to rotate this angle to come here and also rotate this angle to come here beside the yellow one. Okay, that's what I'm trying to do. So the smart ones will probably know um I'm trying to do here by moving this angle here and this angle here. But if you can't get that, so don't worry. I'll show you in a bit. So I'm going to come to these two here and select rotate around point. Then I'll select the red one and then the midpoint. So I'm rotating the red one, the red angle, and I'm rotating it by alpha, and I want it to move this way. So from here to this side. So that is clockwise movement. So okay. Then I select the green one and I want it to move this way. So that is counterclockwise. So I select the green one and then I select the midpoint. Then it is counterclockwise and then the angle is alpha. Because we are using the slider here. So okay. So we have it here. So when I turn the animation on, you can see that the angle, these two angles will move and will come and connect with the yellow one over here. So let's pause the animation. Then let's move alpha to its extreme at the right so that everything is aligned perfectly like this. Now, if you still haven't seen what is going on here, you can see that this angle, when this red angle and this green angle is moved here, beside or adjacent the yellow angle, you see that they form angles on a straight line, right? They form angles on a straight line. So if you draw a parallel line to the base of the triangle, okay, if you draw a parallel line to the base of the triangle, you realize that there will be angles on a straight line at this vertex here. You get an angle on a straight line. And then this red angle here will correspond to this angle over here. But in actual sense, it is what we call alternating angles, okay? Alternating angles. This angle alternates with this angle. This angle, green angle, also alternates with this angle here. And we said alternating angles are equal. So this angle is equal to this angle is equal to this angle. So if this angle is equal to this angle is equal to this angle, and the sum of all these three angles is angles on a straight line, and it is equal to 180 degrees, then when I sum the angles inside the triangles too, it must be equal to 180 degrees because these angles here are the same angles here that are forming angles on a straight line here. So do you see it? So that is why when you sum the angles in a triangle, it will be equal to 180 degrees. Okay, because those three angles can form an angle on a straight line here, and angles on a straight line sum up to 180 degrees. Okay, so this angle alternates with this angle alternates with this, and alternating angles are equal. So if the sum here on this straight line is 180 degrees, then the sum in the circle, in the triangle, sorry, should also be equal to 180 degrees. Okay, so this is a graphical proof of why the sum of the angles in a triangle is always equal to 180 degrees. Okay, all right. So we'll move on. So the next thing we want to look at is theorems in circle theorems. Okay, so some of the terms that we can find in circle theorem. So since we are talking about circle theorem, we know we are going to have circles. But for this particular first one, we are going to use a semicircle. Okay, so let's create a semicircle. So we have this. Then we'll use segments to enclose it. So this theorem that we are trying to prove says that the angle subtended by the diameter of a circle or semicircle is always 90 degrees. So the angle is subtended on the circumference of the circle or semicircle. So we are just using semicircle, but you can use a circle. Okay, but it really doesn't matter, because if it is at this part of the circle, if the angle is created at this part of the circle, you can still pick the semicircle there. If it is located at the bottom part of the circle, you can pick the semicircle there. So we'll just use a semicircle instead of a circle. Okay, don't get confused. So what they mean by the angle subtended by the diameter is that if you pick a point and put it here, so the angle subtended by the diameter just means that draw a line segment from the end points of the diameter to meet that point that you place on the circumference of the circle like this. Okay, now when you use the angle to find the angle here, the angle should be equal to 90 degrees. Okay, so that's what the theorem is saying. The theorem is saying that if you create an angle on the circumference of the circle by connecting a point there to the endpoints of the diameter, the angle that will be formed there will always be 90 degrees. Okay, emphasis on the always. The angle will not change regardless of where the point is, whether the point is somewhere here or here or here. You see, it doesn't change. It will always be 90 degrees. Okay, we can turn the animation on, and you can see that as the point moves along the circumference of this semicircle, it will remain 90 degrees regardless of the location of the point on the circumference of the circle. That is what we are trying to prove here. So I can let's pause the animation. So I'm going to go to object properties just to make the animation a lot better. So um, style color. Okay, so I think I have to select the point. So this is the point. Basic. Okay. All right. So I wanted to change the animation style. Okay. So in the algebra view, in the algebra section, the object properties, that's where you can change the animation style from um increasing to oscillation. Okay. Oscillation is much better because it makes the point to move up and down instead of just moving up or just moving down. So you see it moves, then it goes backwards again. Okay, and that is exactly the beauty we want here. All right, so we are done with the first two. So we have seen the angles of the sum of the angles in a triangle is 180 degrees. And we've also seen that the angle subtended by the diameter at any point on the circumference is 90 degrees. All right, so let's look at another theorem. And that theorem is the main theorem from which this theorem was generated. Okay, this theorem over here was generated. So that one we are going to use a full circle. So circle with center 2 points and create a circle somewhere here. So we don't need a point R. So I'm going into my algebra view. Let's turn the animation off. Algebra view and remove R. Okay, let's move this a bit up to see the full circle. Then we are going to put points here because of animations. I'm going to go to circular arc and create a circular arc here so that I can animate my work nicely. Okay, so I'm creating a circular arc on the circumference of the circle. So there we go. Then I can remove the circle to see the circular arcs I have created. Then I'll go to point and put points on the circular arc. Okay, I'll put points on it. Then now I can bring back my circle and remove the circular arc, not by deleting them, by just unselecting them in the algebra view so that I can have, okay, so these 2 points, you see that it looks like it's on the circle, but it is actually on the arc that I created. But because the circumference of the arc is equal to the circumference of the circle, it lies on the circle. It looks like the point is on the circle. So the next step now is to put a point on the circle itself. Okay, this point is not on the circle, so we have to delete it, undo. Okay, so delete. Okay, so you must make sure it's on the circle. All right. Now all these things you can use the algebra view, the input field to do that as well. Okay, but sometimes it's can be time consuming to use the input field to do all this, but it gives you the best accuracy. Okay. So for this term, we're going to use line segments to connect the point. So this point to this point, then this point to this point, then this point here, that's the center to this point here. Then from Z also we'll connect the line segments to A1. Okay. Then we'll go to angles and find the angle WA1Z, which has a current value of 50.68. Then we'll find the angle that is created at K here, which is the center of the circle, which is currently 101.35. Now, this is where the theorem comes in. So let me move this down a bit. Okay, I'm trying to move this by my mouse pad is a little bit. Okay, so we have this somewhere here. And then let's move this somewhere up. Okay, up is okay. All right, so now I want to do something. I want to find, I want to find um gamma times 2. Okay, so this is where the theorem comes in. So the theorem is saying that given any shape like this in a circle, okay, so this shape is a chord. Okay, there is a chord here. Okay, but we can't draw the segment, so you may not see. But when you draw a segment, so let me draw a segment there. When you draw a segment here, you get a chord. So this chord divides the circle into major and minor sectors. This is the major sector, this is the minor sector. Okay. So the angle subtended by this chord at the center of the circle, the angle, this angle, delta, will always be twice the angle subtended by the same chord, but at the circumference of the circle. So here gamma, okay? So the angle at the center will always be twice the angle at the circumference, okay? And over here, you see gamma is 50, right? Delta is what? 101. And then when I did gamma times 2, which is this epsilon here, gamma times 2, I got the same value as what? Delta. Okay, so when I put my cursor on epsilon, it tells me epsilon is gamma times 2. Okay, so that's what I'm talking about. So the angle here at the center will always be twice the angle here. Okay, so that's the term. That's the term. When you have a chord, the angle subtended by the chord at the center will always be twice the angle subtended by the chord at the circumference of the circle. So since we were able to um, do some, we can set some points on the circular arc, we can turn the animation on, and then we should get a nice movie. So what this is doing is that it is changing the angle here at the center, and then that change is affecting the angle at the circumference as well. But regardless of that, you realize that the angle at the center will always be twice the angle at the circumference of the circle. Okay, so the animation is going all weird, so let me just fix that. So object properties, let's change this to oscillation, and let's do the same for this point as well. So let's change this also to acceleration. Let's turn the animation back on. Okay. Okay. So I think that's okay for that. So we can continue. All right. So now you can see that this term here, okay, this term that we just showed, this one, is actually the bigger term that this one was um gotten from. Okay, so you see that this term is like a subterm from this term here, because this one is saying that the angle at the center is always twice the angle at the circumference. Okay, now when you come here, the angle at the center here is what? 180 degrees, because it is angles on a straight line. So this 180 degrees, okay, that's the angle at the center, is twice the angle at the circumference, which is now 90 degrees. So now you see, so the angle here is 180 degrees. That is why the angle at the circumference is 90 degrees. Okay, so this term here comes from this term. The angle at the center will always be twice the angle at the circumference. So the angle at the center here is 180 degrees. That's why the angle at the circumference is 90 degrees. And it will be 90 degrees regardless of where you put it. The same thing here. The angle here will also remain the same regardless of where I change it to. Okay, so you see it's 35.85 regardless of the position on the cycle. So it can even come somewhere here. Okay, it wouldn't matter. It can even go somewhere here. It still doesn't matter. The angle will still be the same. Okay, so we just have it up there. We just have it up here. Okay, but it doesn't make it different. So let's prove one more term in circle term, and then we'll move on from there. Maybe another time we'll prove some more terms from there. So the last term we'll prove for today under circle term is this term. So that term will also require us to have a full circle. So circle with center through points. This is the center, and I want it about this big. Okay, so C1 should be off. Okay, so we have this circle right here. Now, this term says we should put a chord somewhere there, like the way we did for this. So as a result of that, we are going to, because we want some animations in there, we'll have to put some circular arc, just like we did for the previous one. So this, then center, then a point here, and all the way somewhere here. Then just like we did for the previous one, we can remove the circle and then put a point here and here. That's the arcs. We put points on the arc. Then we can bring back the circle and remove the arcs and the end points. That's D1, E1, F1, G1. So we have these, okay? Right. So now that we have these points here that will help us to do the animation, we can move on to the theorem. So the theorem is saying that if I connect a segment here and then I put some points, so this segment has divided the circle into a major sector and then a minor sector. If I put points on the major sector, so for now, I'm just going to put 3 of these points here. Then using my segments tool, I'm just going to connect the segments so to form 3 triangles. Okay, so this is what I'm talking about. 3 triangles. Okay, now the term here comes in after you go to the angle to so on the angle tool, and then we select or we find the angle of the angle subtended at the circumference of the major sector. So we have these 3 angles here. So let's make them more visible. So let me move this somewhere here. This maybe up here, and the last one up here as well. Okay, so this is where the term comes. The term is saying that the 3 angles here on the circumference of the major sector are equal. So currently you can see here is 45.92, here is also 45.92, and here is also 45.92. Okay, so that's what the term is saying. That if you have a sector that divides the angle, okay, the sector divides the circle into so a chord, sorry, a chord that is dividing the circle into minor and major sectors. That chord, okay, when you subtend an angle at the circumference of the major sector, okay, so it doesn't matter the number of angles you subtend, but all the angles will have equal measure, as you can see here. So with the animations, we can turn the animations on. Then you can see that as the angles change, if I pause it randomly, the angles are still going to be the same. So 24.97 each. If I turn it on again, okay, as it goes and I pause it randomly, the angles will still be the same. So regardless of where it is, the angles will always be the same, okay? Regardless of the chord, the position of the chord, the angle subtended by the chord at the circumference of the circle will all be the same. That's why in this part here, we only use one of them, okay? We only use one here. We didn't create another one because they'll all be the same. So we just use one to show the term here. Okay, so this term is saying that those angles will all be the same. Okay, so um these are all the terms that we will look at for now in circle theorem. Okay? I'm hoping you have learned something very valuable. Now, before we go, we are going to visualize the Pythagoras theorem. Okay, and that's the last thing to do, and then we'll end. Okay, so we will just visualize the Pythagoras theorem, and then we'll end. So let me create new window here. All right, so what we want to do is to create a right angle triangle. Okay, so because we have this grid here, creating a right angle triangle should be easier since I just have to follow the grid. Okay. So they have perpendicular lines in this grid. So I just use the perpendicular lines to create this right angle triangle. And I know it's right angle triangle because if I find the angles inside this triangle, I'll get one of the angles to be 90 degrees, okay? But that's not our interest right now. All right, so this right angle triangle turns out to be an isosceles triangle as well, because you can see that the two sides are equal from the algebra view. A is equal to C, but I don't want that. I don't want an isosceles triangle because the proof has to be random. Okay, this one, some people might think this proof only works for isosceles triangle. So I'm going to increase the point of C a bit. Okay. Now, if I put my polygon to wrap the points up, I should not get two of the sides to be equal. All three sides are distinct. So A is 6, B is 7.21, and C is 4. Okay. So this proof works for all kinds of right angle triangle. It doesn't matter whether two sides are the same or not. And that's what I want to show. So the next step is to, so the proof we are going to do is that the Pythagoras theorem itself says that the base squared times plus the side squared, okay, the length of the base squared plus the length of the height squared is equal to the length of the hypotenuse squared. All right. Now these are length squared. Okay. The term is saying length squared, length squared, length squared. Now when you have a length and you square that length, you get a square. Okay. That length squared is the same as the area of a square. If you have a square and the area is L, then L squared, okay, L squared is the area. So the length is L, then the area is L squared. I hope you get me. If you have a square and the length is L, then the area is L squared. So here we have a length squared here. So we can use a square to represent, okay, the square, and we'll say the length is C, so that C squared is the area of that square. Okay, so what I mean is that we are going to create squares at each side of this right angle triangle. So you can use a polygon tool, regular polygon tool, but we are not going to use that. We will start by using parallel lines. So we'll create a line parallel to this side. That's the height, and we'll create it at point C. Then we use our circle. Okay, so before we use the circle, okay, I think we can use the circle. So I'm trying to get it to be equal measure. So we'll stand at C rather and open the circle to B. Then we can find the point of intersection of the circle and this line right here. Then now we can go back and use perpendicular tool to find the perpendicular of this, because we know a square has 90 degrees. All its angles are 90 degrees. So we have to use the perpendicular tool to get it to be 90 degrees. Then we can use the same perpendicular tool to find perpendicular to this line and at this point here. Now we can remove the circle, then find the point of intersection of this line and this line. Okay, so there are several ways of going about it, because all we are trying to achieve here is to draw a square. So there are several ways to draw that square to have equal lengths. Okay, the length and breadth should be equal, and it must be equal to the length of A. Okay, so with this square we have created has equal length here, 6 as you can see, and that is the same length as A because we created a square using the length of A. Okay, so I can choose to not show the label, okay, so that everything is a lot visible. All right. Now the next step is to create a square so we can remove the lines. So let me actually change this to object type so that I can see everything. So these are the lines. So the next step is to create a square here and here. So let's not waste any time. Let's quickly do that. So just like we did for the first one, parallel lines here, then circle here, open Y to here, then intersect of this line and circle, then parallel lines from here, parallel to this, then parallel this to this point here. And then we have intersect. We find the intersection of this line and this line. And then we have all the 4 points for our square. So let me remove this. Let me remove the lines. Then using the polygon tool, I connect these points. Then the last one, which is this side, which can be a little tricky, but we are going to do it because it is slanted. Okay, so how do we start? Okay, so just like we did for the other ones, we will use perpendicular line and find the line perpendicular to this at this point, perpendicular to this line at this point as well. Then using our circle tool, we can draw circle this big. Then using the intersect tool, so let me pull everything down, okay, so that we can find it. So using the intersect tool, we find the points of intersection of these two. Then we can go back to perpendicular lines, then find the line perpendicular to this at this point here. Then we can remove the circle, find the intersection of these two lines, then use the polygon tool to draw the last square. Remove the lines, and we are done. Okay, so what have we done? What we have done is that we have created a square on each side of this right angled triangle, okay? And that is exactly what we wanted to do because we want to relate the, length squared in the formula. We want to relate it to squares because if the length squared can be related to the area of a square. So that is what we have done, okay? So we have created the squares on each of these sides. So the next step now is to just find the area. So let's go to the angle tool and find the area of these three sides. So you realize that this area plus this area will give us the area of the hypotenuse. So the area of the height here is 16. The area of the of the square that is formed on the base here is 36. And when you add 36 to 16, you get 52. Okay, that's why we are saying that this squared plus this squared is equal to this squared. Okay, this length squared is the area for this square here. This length here squared is the area of this square here. And then the length of the hypotenuse squared is the area of the square that is formed here. So when I add these two areas, it's equal to the area here. And this is a visual representation of the Pythagoras theorem. And these particular values here don't really matter, because if I increase the length of of any of the sides, okay, the areas will change because the squares will change as well. And as the squares change, the area changes and the value will be the same. This plus this will always be equal to that. Okay. All right. So this is a visualization. All right. So a simple proof for the Pythagoras. Thank you very much. And I hope to see you in the next video. Thank you.